Today we shall study about wave of text. In this chapter we study about Doppler effect. We know that one should be careful in constructing the wave fronts if the source or the observer is moving. For example, if there is no medium and the source moves away from the observer, then the latter wave fronts have to travel a great distance to reach the observer and hence take a longer time. The time taken between the arrival of the two successive wave fronts is hence longer at the observer than it is at the source. Thus, when the source moves away from the observer, the frequency as measured by the source will be smaller. This is known as Doppler effect. Astronomers call the increase in wavelength due to Doppler effect as a redshift. Since a wavelength in the middle of the visible region of the spectrum moves towards the radiant of the spectrum, when waves are received from a source moving towards the observer, there is an apparent decrease in wavelength. This is referred to as a blue shift. For velocity small compared to the speed of light, we can use the same formula which we use for the sound waves. The fractional change in frequency delta nu by v is given by minus v radial by c, where v radial is the component of the source velocity along the line joining the observer to source. Relative to the observer, v radial is considered positive when the source moves away from the observer. Thus, the Doppler effect can be expressed as delta nu by nu or minus v radial by c. The formula given above is valid only when the speed of the source is small compared to that of light. A more accurate formula for the Doppler effect, which is valid even when the speeds are close to that of the light, requires the use of Einstein's special theory of relativity. The Doppler effect for light is very important in astronomy. It is the basis for measurements of the radial velocities of distant galaxies, coherent and incoherent addition of waves. The entire field of the interference is based on the superposition principle, according to which at a particular point in the medium, the resultant displacement produced by a number of waves in the vector sum of the displacement produced by each of the waves. Consider two needles S1 and S2 moving periodically up and down in an identical fashion in a trough of water. They produce two water waves, and at a particular point, the phase difference between the displacements produced by each of the waves does not change with time. When this happens, the two sources are said to be coherent. Let H by 1 barabar displacement produced by the source S1 at the point P barabar A cos omega t, by 2 barabar A cos omega t. So, by barabar by 1 plus by 2 barabar 2A cos omega 2. Since the intensity is proportional to the square of the amplitude, the resultant intensity is given by I barabar 4 I naught, where I naught represents the intensity produced by each one of the individual sources. I naught is proportional to A square. In fact, at any point on the perpendicular bisector of S1 and S2, the intensity will be 4 I naught. The two sources are said to be interfere constructively, and we have what is represented to as constructive interference. The figure A shown for constructive interference. Now, where we have used the fact that a path difference of 2.5 lambda corresponds to a phase difference of 5 pi. The two displacements are now out of phase, and two displacements will cancel each out to give zero intensity. This is referred to as destructive interference. Average intensity I is equal to 4 I naught is equal to or greater than or smaller than cos square phi by 2. When the phase difference between the two vibrating sources changes rapidly with time, we say that the two sources are incoherent. And when this happens, the intensity just add up. This is indeed what happens when the two separate light sources illuminate a wall. Interference of light waves and Young's experiment is shown in figure 1 and 2. Two-slit experiment it is called. The British physicist Thomas Young used an ingenious technique used to lock the phases of the waves emanating from S1 and S2. He made two pinholes S1 and S2 very close to each other on an opaque screen N. These are illuminated by another pinholes that was in the turn, lit by a bright source. Light waves are spread out from S and fall on both S1 and S2. S1 and S2 then behave like two adherent sources because light waves coming out from S1 and S2 are derived from the same original source, and any abrupt phase change in S will manifest in exactly similar phase changes in the light coming out from S1 and S2. Thus the two sources S1 and S2 will be locked in phase. It means they will be coherent like the two vibrating needles in our water. Wave example. Thus spherical waves emanating from S1 and S2 will produce interference fringes on the screen GG'. The positions of maximum and minimum intensity can be calculated by using the analysis, where we had shown that for an arbitrary point P on the line GG' to correspond to a maximum, we must have S2P minus S1P over N lambda. Now S2P का whole square minus S1P का whole square over D square plus S plus dy2 का whole square minus D square plus S minus dy2 का whole square बराबर 2SD, where S1 S2 बराबर D and OP बराबर S. Thus S2P minus S1P बराबर 2SD बटा S2P plus S1P, इसलिए S2P minus S1P बराबर S divided D. Hence, we will have constructive interference resulting in a bright region between S barabar X and barabar N lambda D by D. On the other hand, we will have a dark region near S barabar X into N barabar N plus 1 by 2 into N lambda D by D for the dark region. For the bright region, S barabar N lambda D by D. Thus, dark and bright bands appear on the screen. Such bands are called fringes. The dark and bright fringes are equally spaced, and the distance between the consecutive bright and dark fringes is given by fringe width beta barabar xn plus 1 minus xn or beta barabar lambda d by d. Expression from fringe width, the fringe width will strictly be hyperbola.